Okay, so this one will be kind of a short one here, where we just kind of review a little bit about what we know about plane elasticity. So from either mechanics of materials, or if you take an elasticity class, we know Hooke's law. And in particular for plane problems, plane stress, for example, we would have sigma x and sigma y and tau xy. But sigma z, tau xz, and tau yz would be equal to 0. So in this case, Hooke's law reduces down quite a bit. We have epsilon x is equal to sigma x over E minus nu sigma y over E. Epsilon y is equal to sigma y over E minus nu sigma x over E. And the shearing strain gamma xy is tau xy over G, where we have an isotropic material, behaves the same in all different directions, and we can calculate our shear modulus G by E over 2 divided by 1 plus nu. We have strain displacement equations. If we know the displacement fields, then we can find that the epsilon x is the partial derivative of u with respect to x. Epsilon y is the partial derivative of v with respect to y. And gamma xy is equal to the partial derivative of u with respect to y plus partial derivative of v with respect to x. I'm not deriving those. I derive those in the class in elasticity, but I'll refer you to an elasticity book if you need. And then it turns out, since these are functions of two variables and we have three relations here, there's a certain connection among these. That's called the compatibility conditions. If we were to take second derivatives of these strain components, the second partial of epsilon x with respect to y twice would be plus the second partial derivative of epsilon y with respect to x twice would be equal to second partial of gamma xy with respect to x and y. This is known as a compatibility condition. And physically, the way to think about compatibility is that if you have a certain particle, that particle can't split up into two pieces, nor can two particles collapse and be in one point. So these are continuum assumptions, and they're very good, particularly at the macro scale. Now, if you go into atomic particle physics, then we deal with things differently. But at a continuum level, we're talking about the grain size of a material, or even within the grain, arrays of atoms, groups of atoms, then this is a pretty good way to deal with what happens inside a material. Things just don't cleave in half. Now there's a topic called area stress functions that we go into detail. If you're taking a class in fluid mechanics, you might talk about potential flow of a fluid, in which velocity fields are derived from a potential. Well, this is a little bit different, but the same sort of idea. In stress fields that are derived from a potential function, we would use area stress function. And I used a different symbol on the previous page, previous discussion, but typical symbol for an area stress function is phi. And it works out such that if we can find a valid area stress function, then sigma x, the stress field in the x direction, would be the the second partial derivative of phi with respect to y twice. The stress in the y direction would be the second partial derivative of phi with respect to x twice. Okay, notice that difference there. Here's the x stress, but it's the partial with respect to y. Here's the y with but it's partial with respect to x. And then the shearing stress could also be derived from that same potential function, but the way it is the second partial derivative of phi with respect to x and y. Now, if the biharmonic equation is satisfied, del forth phi is equal to 0. Then it turns out that equilibrium equations compatibility and isotropic stress-strain relations are satisfied. And this is for 2D elasticity problems only. There is no three-dimensional analog for Airy's stress function. Now for completeness, let's go ahead and write down the equilibrium equations for plane elasticity. That would be the partial derivative of sigma x with respect to x plus the partial derivative of tau xy with respect to y. If we neglect body forces, those would be equal to 0. And then the partial derivative of tau xy with respect to x plus partial derivative of sigma y with respect to y. Again, if the body forces are equal to 0, that would be equal to 0. And those are equations that must be satisfied if the stress field maintains equilibrium. All right. So again, just to restate what we had mentioned in the previous part, if we can find a function that satisfies the biharmonic equation, we know we have some sort of solution that works for an Airy stress function potential. And we can find stress fields that go along with that. Now, some of these stress fields are interesting and some of these are not. One not interesting stress field would be the function phi is equal to 0. If phi is equal to 0, then sigma x, sigma y, and tau xy are all equal to 0. While it's true that if you have a body that has no stress in it, you automatically satisfy equilibrium and compatibility conditions, this really isn't a very useful thing to look at. So then you start getting into higher order terms. And in theory of elasticity, we look at polynomial functions for stress functions, and they would have to be at least fourth order or higher functions of x and y. And in this class, we're going to take a look at complex functions. And that complex functions that are Airy stress functions really open up a wide class of problems that we can solve. But we need to figure out, again, what exactly we have solved. So we need to take a look at the boundary conditions of the problem. What are the stresses on the edge of the body? In our plate with a hole example, we had the stresses that were in the vertical direction, off at infinity in the y direction. So if we have a stress function that works for a plate with a hole, we need to have the limit as we get to infinity that the y stress equals to that remote nominal stress. And then whatever else happens around the hole. The edge of the hole, that's traction free. And so we wouldn't have any stresses around the edge of the hole in the radial direction or in the hoop direction for the shearing stress, but we could have hoop direction normal stresses at that edge of that hole. So a lot of things depend on the boundary conditions and what kind of problem that you're actually trying to solve. All right, so in the next part, we're going to take a look in particular at the Westergaard function.